afternoon and good evening. Welcome to Statistics 1001. My name is Ian Coates. This will be the second PowerPoint for the Week 9 series here. Hopefully there you enjoyed the confidence interval. And please note that we'll make 3 videos there today. The one there you just watched. 9B here will be on hypothesis testing with means of sample. It's just kind of a recap, okay, of what we've been doing, okay. We are going to move on to newer things sooner than later, but right now we're on the means of samples. All right, and as well note, please, there will be a third video, okay, which we'll talk about there. We'll go over the assignment 2, okay. No further ado, let us move on, shall we? All right, let's get this all organized. Let's go. So, logic of hypothesis testing. A lot of this there you will have seen there before. It's just kind of review because I know this stuff is very, very, very abstract. So, then we're talking about the logic of hypothesis testing here. The subtleties there in logic are important to science as well as any type of legal system. And we've seen this there, the whole idea, the 2 kinds of errors there that we can make, okay? But when you're talking jurors in a trial, okay, a murder trial of something there, they're not asked there to identify there if the defendant is innocent, because that is an impossible task. The only thing there that the judge is asking the jury to decide is whether you look at the rejecting the null hypothesis and retaining the null hypothesis. What do these actually mean? Okay, you can't prove if anyone's innocent, but what you can decide is whether there's enough evidence to make them guilty. And if there's not enough evidence to prove that they are guilty, then they're not. Okay, and this is kind of the thing here. In our legal system there, the null hypothesis is that the defendant is not guilty. You are supposed to retain that. That is where we are at, retaining the null. That's why it's such an important concept. That is our pillar of strength. Okay, and we have to, the whole idea of not rejecting it or rejecting it is all based on the evidence. Jurors are supposed to stick with the null hypothesis until there is enough evidence to reject it. Scientists are supposed to do the same thing. Okay? So, scientists typically have to decide between 2 types of possibilities, type 1 and type 2. We've talked about these. The bad news is that we have to make error. If we're going to take a sample and project it onto a population, we have to work with error, okay? But we know the probability of this error, okay? And therefore now we can quantify it, okay? You'll remember there your type 1 error, an error in statistical inference that occurs when the null hypothesis is true but is rejected. Reading too much into the data. Okay? And now this means there that you're zoomed out. You're on low magnification. You're seeing too much of the Drosophila. Okay? You're reading too much into the information. There's too much information here. The facts are starting to clutter your judgment. You need more zoom. But the problem is, you could run into a type 2 error. This is an error in statistical inference that occurs when the null hypothesis is false, but is retained. You're not seeing enough of the data, and this is where you've got too much zoom. This is where you're on high magnification. You're only seeing the Drosophila's leg. You can't see anything else. It's cluttering your judgment. You're making a wrong diagnosis. Okay, type 1, type 2. Okay, we've done these there. You guys, you will see them again, all right, but they're very important. How much zoom do we utilize? Too much zoom, I'm losing information. Not enough zoom, I'm getting too much. And both are confounding my judgment. Okay? Let's go. So, evaluating hypotheses here, we can quantify the risk by taking advantage of the statistical properties of the Gaussian distribution. You got it. In particular, we can determine whether a particular score falls in the so-called critical region, the area in the distribution that contains extreme scores. And the whole reason why we use the extreme, like this is a two-tailed, but it can be a one-tailed, one-tailed negative, one-tailed positive. But the whole reason why we use these extreme scores, right? And we're not interested in all of the rest of the information here. Why? Okay. The area in the distribution that contains these extreme scores that are very unlikely to be observed if the null hypothesis was true. That's why we take these extreme scores, because at random, these ones here would be very unlikely if the null hypothesis was true. And remember, that's what statistics is about. You got to deviate away from the null if you're going to get anything done. Okay? The critical region is also called the rejection region. That is, if a sample mean falls in the critical region, the null hypothesis is rejected. So, yes, we might make a type 1 error, but typically the probability of such an error is only 5%. That is, we set our alpha level to 0.05, meaning that we only have a 5% chance of rejecting the null hypothesis that should have been retained. So again, there's your 5% standard error, 5%. This is the best that we're going to get. So in some cases there, we might choose to minimize the risk of a type 1 error and get a more stringent alpha. You guys have seen this one there before. There's your 95, there's your 99. This is 900, and this is, 1 in 1,000. We don't use that one there, but that you really can't get any more stringent than that. Okay. Okay, here we go. Remember, step 1, state your population 1, population 2. Remember there, population 1 is who you are looking at. Population 2 is people in general. And then there's your alternative hypothesis and the null. The null hypothesis, I always write first because it's the easiest. No difference. Women at a community college are equal in height to women in general. No difference. Alternative hypothesis here, women at a community college are not equal in height to women in general. Okay? Good. Sorry, we missed one. Yeah, I was wondering, we're going into step 1 here. Yeah, let's go back and read the question and then come back here, eh? Oh, Jesus, Murphy. A researcher hypothesizes if there is a difference in mean height of women at a particular college. Randomly sampled 60 people from a population of women at a particular community college to measure height to determine if there was any variation in the height of women at this college as compared to the general population. There's your significance, okay, 95%. Information provided, okay, we got the population mean, 63.8 inches. We have the population standard deviation, which is 2.5, and that's about this population here, right? And then our sample, 60, and our mean is 65. Now, remember, because this is the mean of means, right? The DOM, distribution of the means. I'm not going to compare my sample against this one. I got to compare my sample against this one because this sample theoretically came from here. It had to have come. There is a distribution. We just don't know what it is yet. Okay? But we do know there, remember the dice from last week's PowerPoint there? The whole idea there that this distribution is very narrow. All those 1 1s and 6 6s, they get canceled out. And now this is the whole meat of it right here. So you'll see there, and we'll apply this there for the assignment as well. When you're asked there to draw the 3 distributions and provide 2 bits of information for them, these are the 3 that I'm looking for. Okay? And in this particular question here, all I gave you was 2 bits of information here, and I gave you 2 bits of information here. Go for it. Now let's have a look. So step 1, we've looked at it, right? There's your 2 pops. Identify them. Here's your 2 hypotheses. Okay, your alternative and your null. Go for it. Let's go. Step 2. All right. Now, this is kind of where we all put it together. And in this case here, it's a bit of a pain in the butt because I gave you the standard deviation here for this pop. I got to find I need to find all the information there for this guy here, my comparing distribution. So let's have a look here. Determine the characteristics of the comparison distribution. Okay? The comparison distribution is a distribution of means of samples of 60 individuals each. So this is hundreds of millions of samples of 60 individuals each. Theorize, right? So the mean here of this population is 63.8 inches. Okay, so therefore the mean of this population will be 63.8 inches. Okay, right there. The population mean of means, the DOM, is equal to the population of means. So that mean, 63.8, is that mean there. All right. The problem is trying to figure out the standard deviation. I gave you the standard deviation here. And you got to take that standard deviation and find the standard deviation over here. Now, of course, this standard deviation will be much bigger than this one because look how tight this one is, right? So you take your standard deviation. You got to square it to get your variance. And then divide by your population or your sample size, which is 60. So you have a look here. Standard deviation, which was given. Population standard deviation right there. And then you square it to get the population variance, which is 6.25. And then you divide it by 60, which is your sample size, and you get a population variance for the DOM at 0.1. All right? And then you square root that to get the standard deviation of the DOM, which is 0.32. And don't worry here, this number here is smaller than this number. Don't worry, the math adds up. Okay? The shape of the distribution will be approximately normal because we have a sample size that is larger than 30. We have 60. So we are good to go. So now we have our population mean, population standard deviation, which was given. We have 2 bits of information here for our sample, and now we have 3 bits of information here. We have a population mean, which is the same. We've actually calculated the variance, which was that one there, and we've, that was for this one here. There's my variance here for the DOM, and then we actually have our standard deviation of the DOM. Okay, so there's lots of information here, lots of marks to go around. So, step 3, determine the cutoff sample score. So if you go back to the question, that is the key. A researcher hypothesis if there is a difference. Not looking for higher, not looking for lower. Is there a difference? Okay, so if there's a difference there, we're just looking for changes up or down. It'll be two-tailed 95%. Okay, you could just look right here, two-tailed 95% plus or minus 1.96, or you could go back. Okay, 95%. Okay, so that means 2.5%, 2.5%. So that'll be 47.5%. You just go 47.5% and you find your number. Either way, these ones here, I just gave it to you in the chart because it was kind of nice, but you can still figure it out old school like that. Okay? So, there's your cutoff scores, plus or minus 1.96. All right. Step 4, everybody now zed it up. So you plug in your information. Okay. So what do we got going on here? My population mean, okay, 63.8. And my sample mean is 65. And I've got the population standard deviation here, but the standard deviation there of the DOM is 0.32. All right, so we got 65 divided by 63.8, minus 63.8. That's my mean of my sample, and this is the mean of my DOM. Okay, divided by the standard deviation of the DOM, which is 0.32. Okay, 0.32. And you get a z-score of 3.75. Now, what does all that mean? Step 5, this is where we decide to reject or accept. And you'll see here 1.96, 3.75 positive point plus 3.75. That's way out here. So we have to reject the null hypothesis, and the findings there support that there is a difference in these two populations. Okay. Moving on here, and this is where we kind of tie back into estimation and confidence intervals here. Okay, Z-tests are not often seen in research, okay, because we really don't have that original population to fall back on. So that's why we use these confidence intervals. They're becoming more common, all right. Estimating the population mean based on the scores in a sample is an important approach to experimental and survey research. When the population mean is unknown, the best estimate of the population mean is your sample. And that's kind of, like you have to think about it. If you just created a new drug that's going to, lower people's blood pressure, well, you just created this drug. It's never existed there before. So what population are you going to draw from? And in a lot of times there, the best estimate of the population is your sample mean. Okay, so it's kind of tough, and then that's the whole idea of standard deviation and standard error. In order to project this hypothetically, logically, scientifically onto something there that really doesn't exist, you're going to have a little bit of error. The accuracy of the population mean estimate is the standard deviation of the distribution of means, also called the standard error. So have a look here. Upper and lower value of confidence intervals. We used to get a sense of, these are used there to get a sense of accuracy. Okay. Confidence. Remember, we talked about this there in the last video there at the end. The whole idea, is there 68% confidence. Well, it's not really a great confidence. 68%. I'm not really that confident, but it's a pretty tight window. I can increase my confidence to 95%, but my window is going to get wider. My area, the range of scores. So 95% confidence there. These are the numbers we're looking at. 99% confidence. Okay, that's what we will be looking at there. Let's have a look here, shall we? So from the original, we looked at, I think it was height. This original question right here. We're looking at mean height there at women at a particular college. And we found that information already. And so the population mean is 63.8 inches. Standard deviation is 2.5 inches, right? The sample mean was 65. Sample size was 60. That's all the information there you got, right? And we found all that information there. There's your variance of the DOM, okay? And we got that number there. Remember, we calculated 2.5, squared it to find the variance of the population divided by the sample size. There's my variance of the DOM. We square root that variance and we get 0.32, right? Didn't change anything. Everything's the same as there before. Well, here's that formula there from week 3, okay? Finding the raw score from the Z. You're going to find an upper and lower level. And these are the exact same numbers there that we saw there from the first PowerPoint that didn't make any sense, but hopefully there they make sense now. So using the information there that we calculated, there's your standard deviation, the mean of your sample, there's the mean of the population of the DOM, and your Z-score. You figure it all out and away you go. Okay, so there's your Z-score there. Now remember, lower limit might be negative. And then there's your standard deviation, 0.32, plus the mean of your sample, not the mean of the pop. And there's your lower level, 64.17, your upper level, 65.83. So now we've got an upper level and a lower level that our sample came from with a 99% confidence. Okay? Let's go for another one here and then we're done. A researcher wants to know if children who participate in after-school programs have a higher IQ score at P is less than 0.01. A sample of 35 randomly selected public school students are chosen from an after-school program and tested. The results were, okay, your population mean is 100, your standard deviation of the population is 15, your sample size is 35, and your sample mean of your population is 107. All right, let's try this out. So again, restate. Okay, there's your population 1 and population 2. Population 2 is always everybody. Population 1 is who you're looking at, your sample. There's your alternative hypothesis and your null. Null, no difference. Please copy this style. I like words. Good. Your alternative hypothesis states that there is a difference. Okay? Good. And children in academic after-school programs will have a higher IQ. We're not looking for a difference. We're looking for higher scores. Education, we only modify education to improve students' scores, right? Okay. So, example there for step 2, determine the characteristics of the comparison distribution. Remember, you have your population, your sample, and your DOM. We need to figure out the characteristics of the DOM. So population mean is 100, which will be the same as your DOM. Okay? Here's the population variance, okay, which was 15, right? 15 is your population standard deviation. Okay? So 15 squared, that's your population variance. Sample size 35. So take your variance, 225, divide it by your sample size. You get a DOM variance of 6.43. Okay? That means your variance of the DOM. And now we square root that and we get the standard deviation of the DOM. And that gives us 2.54. So now we have all the information there that we need to calculate this up, and the shape of the distribution will be approximately normal because it's greater than 30. So, step 3, determine our cutoff values. So we're looking at 99% one-tailed because we're only looking at higher. So, and you could do it like this right here. There's your 99% one-tailed. So we're looking for positive 2.33, or you could go old school and calculated it out. So 99%, so that's 50. This would be 49, and that would be 1%, right? So there's your 49.1, 2.33. It's right there, okay? So this is what we're looking for. There's our critical value, critical region. And step 4 is everybody Z it up. So there's your Z, there's your mean minus your mean of the DOM, and there's your mean of your standard mean of the standard deviation of the DOM. Whew! Come on, Ian, get it together. So 107, that's your sample mean, minus 100, which is the mean of the DOM, all divided by 2.54, which is the standard deviation of the DOM. And we get a Z value of 2.76. So what does all that mean? There's your cutoff score, 2.33. Z is 2.66. Reject the null. The kids in the after-school program most definitely have a higher IQ score than children who do not. And that's one of the things there I want to talk about for the assignment, is that we want you guys to make an opinion, make a judgment call. And now figuring on and moving on here, step 5, now we'll figure out these confidence intervals for this particular example here. And that's what we're looking for there. Okay. Good. And we'll do this there at a 95. And in this case here, we're using a 95% confidence interval. Okay, and we're just playing with numbers there. I just want to show you guys what's going on. Okay, so with a 95% confidence, we are confident there that our mean of our sample, okay, falls within this range. We had a mean of sample of 107. The mean of the population was 100. And we are confident that our population, our sample, came from a population that had lower limit and upper limit of these two numbers here, 102 to 112, with 95% confidence. All right, so that's where we're at. I hope you guys enjoyed it, and now we'll move on to the third PowerPoint about the assignment.